Remember the days when everything was simple and we were told that all gases behave identically and they're all ideal, and we have this ideal gas law that works for all the gases, and you can just plug numbers in and solve for P or V or T, and everything was great, and you could just go on with your day. And remember those days? Then your teacher comes back and says, well, there are some gases that don't really behave the way we think they should behave, and they tend to not follow the rules a little bit, and so the ideal gas law becomes more of like an ideal gas suggestion for some gases. And that's true. Some gases do behave badly. And we have to be able to answer some questions about those. So let's get into it. The nice thing about gases is that under normal conditions of temperature and pressure, like we might see in a laboratory, most gases do behave fairly ideally. And so the ideal gas law does work well for us. But there are a couple of situations in which gases don't behave very well. And we're going to highlight those as a review. Just a quick note, this is just a quick review. If you'd like more information on real gases and why they are the way they are, you can check out my other videos in the Unit 3 playlist for AP Chem. Um, okay, so let's get started. Under gas behavior deviates from ideality at low temperatures and high pressures. Okay, so why is that? First of all, at low temperatures, molecules move slow enough to interact more with each other. So intermolecular forces do exist. That's why the unit that we're in right now. And all molecules exert some sort of intermolecular force with all the other molecules around it. It might be a small force, it might be a large force. But if the molecules are moving really fast and they fly past each other, there's not a lot of time for that force to take effect and do anything. But if the molecules are moving slower, like at a really low temperature, they are moving slowly past each other, and then that force of attraction can apply a little bit more. And maybe those molecules stick together a little bit more. And when gas molecules actually stick together because of that attraction, their two molecules suddenly become one gas molecule, and the pressure actually drops a little bit because of that. So sticking together causes pressure to drop, as well as probably a little volume drop as well, because the overall volume doesn't need to be as big. At high pressures, the volume of the particles becomes a greater fraction of the overall volume. So what if you have a gas that's at a really high pressure and you're just packing molecules in like crazy? The more you get in there, the more chances they have to interact with each other. They're closer together, they're bumping up next to each other, and they are able to apply their intermolecular forces a little bit. And the actual volume of the particles, which we generally assume to be zero at normal conditions, it actually becomes a greater fraction of the overall volume. And so it messes with the volume calculation a little bit. Generally, molecules with greater intermolecular forces behave less ideally. So if you're comparing gases at the same conditions, same temp, same volume, same pressure, one may behave more ideally than another if it has weaker intermolecular forces and weaker attractions, whereas another one might have stronger intermolecular forces and might behave badly because of that. Now let's start in on some types of multiple choice questions that you might see on your exams regarding this. It should be noted that there is an updated version of the ideal gas law that takes care of real gases. It's called the van der Waals equation, and it contains a couple of correction factors for pressure drops and volume changes based on the volume of the particles. The nice thing is that a bunch of years ago, they took it off the AP chemistry exam. So if you're taking AP chemistry, you don't have to worry about it. You will probably need to understand the concepts, though, behind it. So no math, but just concepts. Let's check it out. So here it says, under which of the following conditions of temperature and pressure would 1 mole of the real gas carbon dioxide behave most like an ideal gas? So when it's trying to get most ideal, you're trying to minimize the attractions, the chance of attractions between them, and maximize the space between those molecules. So we have 100 Kelvin and 800 Kelvin. And then a difference in pressure of 0.1 atmosphere and 100 atmospheres and 1 atmosphere. So which possible combination? So first, I'm going to look for the highest temperature. The higher the temperature, the faster the molecules are going, and that's a significant temperature increase. And so they're going to fly past each other and not stick to each other as much. And then I'm going to look over here and I see pressure of 0.1 atmospheres and 1 atmospheres. Generally, the lower the pressure, The greater the space between the molecules and less interactions between the molecules. And if we're looking for most like an ideal gas, that'll be choice letter C on this one. So highest temperature and lowest pressure at that temperature gives you the best results. And let's do another one real quick. Here's another diagram. The diagrams above represent two samples of xenon gas in containers of equal volume at 280. Which of the following correctly compares the two samples in terms of their deviation from ideal gas behavior, and explain why? All right, which one would deviate more? Sample 1 would deviate more, sample 2 would deviate more, sample 2 would deviate more. A couple of reasons: because the xenon atoms are closer together, the average speed of the xenon atoms is less, leading to an increase in intermolecular attractions. The gases in both would show the same deviation from ideal gas behavior. So what do you think? If you saw these four choices, which one would you pick? They are at the same temperature, so the average speed, remember, and they're the same thing, so let's not pick that one. They would not show the same deviation from ideal behavior. I'm looking at this one. There's more molecules and they're closer together on average. And so that leads me to answer B. The xenon atoms are closer together, leading to an increase in intermolecular attractions. All right, so that's letter B. All right, one more, and then we'll do a pause the video moment. At constant temperature, the behavior of a sample of real gas more closely approximates that of an ideal gas as its volume is increased because collisions with the walls of the container become less frequent, average molecular speed decreases, average distance between molecules becomes greater, average molecular kinetic energy decreases. Okay, it's not D. We've been told to laser focus that kinetic energy is based on temperature, not the other stuff. So, boom, let's get rid of that one. And in this case, you're increasing the volume of a sample of gas. Now the molecules have more space, and the average distance increases, and it behaves more ideally because there's less interactions between molecules. Okay, your turn. The next one is our pause the video moment. A vessel contains argon at high pressure. Which of the following statements best helps to explain why the measured pressure is significantly greater than the pressure calculated using the ideal gas law? All right, take a moment, pause the video, and see back here in a couple of seconds. As you look through the choices, it comes at high pressure. The volume of the particles becomes a more significant fraction, sorry about that, of the total volume. And they would actually then push on the side of the container a little bit harder, making the total pressure a little bit higher than what we would expect. So good job on that. Now let's consider some questions where we have to know a little bit about the molecular shapes and the polarities and intermolecular forces of the molecules. Take a look at this one. This one includes some information about NH3, ammonia. And we've got samples at different pressures, and ideal gas law would calculate these volumes in liters and then the experimental. Okay, so what is this trying to show us? Showing us at low pressures, the experimental data kind of matches the ideal gas data, so whatever was calculated here. At higher pressures, we get a slight deviation from ideal gas law behavior because the pressure is increasing. And at 8 atmospheres, now we get a significant deviation from the ideal behavior. So the question is, why? The pressure of the sample of NH3 was changed by adjusting the volume of the container. The experimental volumes that were needed to achieve the desired pressures were different from the volumes predicted by the ideal gas law. Which of the following best explains the difference? Okay, so here we have the bottom two, check them out, average speed. And remember, that depends on temperature, and we're not doing anything with temperature up here, so let's get rid of those. Now, A and B talk about attractions and repulsions. The attraction between the molecules becomes significant at higher pressure, or the repulsion between molecules becomes significant at higher pressure. Well, here it's helpful to know that ammonia, and you may have to draw this. Sometimes you're just given the formula, and if you're not sure, take a moment and draw the Lewis structure for NH3. And if you do that, I'll do it quick, you will find out that NH3 is a trigonal pyramidal shape. And so it's going to be polar. In fact, it's going to be very polar because it's got hydrogen bonding with the hydrogens and the nitrogens there. That makes it polar, strong attractions, And at high pressures, those strong attractions become more prevalent. So, because they're packed in there and they're getting up close to each other, interacting and attracting to each other. So, there we go. Which of the following best helps explain why a sample of CH4 is closer to the pressure predicted by the ideal gas law than a sample of NH3, which has a similar molar mass? I did this one on purpose in this order. Take a moment and see if you can pause the video and guess the correct answer, and I'll see you back here in a couple seconds. And if you paid attention in our last question, we saw that NH3 molecules are polar, while CH4 molecules are not. You may have to spend a moment just drawing them to see. Is CH4 polar? Does it have a lone pair? No, it doesn't, so it's nonpolar. And so the greater attractions between NH3 molecules cause the molecules to collide with the walls of the container with less force. Well, yes, this is polar. And the greater attraction, so they'll be too busy attracting with each other and maybe hitting the side of the container with a little bit less force. We're not talking about molar mass, hydrogen atoms, or CH4 molecules being larger than NH3. They're going to be very similar in size. So A is your correct answer there. All right. Which of the following best explains why H2 behaves more ideally than most other gases? All right, so what's so special about H2? H2 is a very, very simple gas. It's only got two hydrogens in it, and each hydrogen only has one electron. So I'm thinking and visualizing this molecule. It's a small, non-polar molecule with very few electrons. So its London dispersion force is going to be very low. So the number of particles in a given volume is smallest? No, that's not right. Collisions between gas particles in the walls of a container are more frequent for smaller molecules. Yeah, they do have a higher velocity, and that's great. But they hit the side of the container with the same force because even though they're smaller, they're going faster, their pressures would be the same as other gases. Average kinetic energy at a given temperature is large. No, temperature is a measure of kinetic energy, and so at a given temperature, they'd have the same kinetic energy as other gases. But letter D, the intermolecular attractions between hydrogens are weak because the electron clouds are small. And so that's why it behaves most ideally. Okay, your turn. Another pause the video moment. CCl4 deviates more from ideal gas behavior than CH4 does. Which of the following statements best explains this observation? Take a moment, pause the video, and I'll see you back here in a couple seconds. All right, and if we thought about last question, applying it here, the London dispersion forces between CCl4 molecules, they will have the same shape. They'll be tetrahedral if you drew them, and non-polar overall. But CCl4 has a lot more electrons than CH4, and so its LDFs are going to be much, much higher. Okay, good job on that one. Couple more. A 1 liter sample of a pure gas is found to have a lower pressure than predicted by the ideal gas law. So something's going on. It's not getting up to the pressure we would expect. The best explanation for the observation is that the molecules of the gas, do they have a combined volume that's too large to be considered negligible? Do they have a low molecular mass and therefore do not strike the container walls with much force? Are attracted to each other and do not exert as much force on the container walls as they would if they had no mutual attractions? Or are attracted to the sides of the container and strike the container walls with more force than expected? Well, it's a lower pressure, so I'm going to ignore that last question because more force would mean a higher pressure. But again, you have to imagine molecules that are polar sticking together, and two molecules then become one molecule, and so you would end up with a lower pressure on that. So there you go. All right, we're almost done with this episode. The ideal gas law best describes the properties of which of the following gases at 0 degrees and 1 atmosphere. And they give us a list of formulas. And you might look at this list of formulas and be like, I don't know. How am I supposed to know this? Well, if you're in doubt, draw them. Make sure you get a good Lewis structure on them. And we're looking for the ideal gas law working the best. We're going to try to get the one that is least polar, have the weakest intermolecular force, and they won't stick together as molecules that much. Smaller molecules also play a part. And if you drew these, you would find this one is polar, this one's polar, This one's polar, and this one is non-polar. If you need a refresher on drawing Lewis structures, I have a whole series of those in one of the other playlists for Unit 2. So non-polar molecule, nitrogen, weakest intermolecular force, the ideal gas law will apply the most there. And we're going to end this episode with another pause the video moment, very similar question. In this one, which of the following gases deviates most from ideal behavior? Take a moment, draw them if you need to, pause the video, and I'll see you back here in a couple seconds. If you drew these molecules, you'll find only one of them is a polar molecule. And so we're going for the most polar molecule, and that is this one. SO2 has a bent shape to it and a lone pair on that central sulfur, making it a polar molecule. The rest of these are nonpolar and have very small electron clouds. So we got through some questions on real gases and how they deviate from ideal gas behavior. Sometimes they behave badly, and we have to be aware of that and why. So I hope you found this helpful. If you have any questions, send them to me in the comments. And in the meantime, happy studying and have a great day.